Okay, let's quickly try to get some learning value from that quiz. Let's ask the question. There are 5 addressing modes in the MIPS processor. 2 of them are used to address code, that is to fetch an instruction, and 3 of those are used to fetch data. Okay, that makes sense. Those are the things that processors need. They need to get code so they can execute the next instruction, and they need to get data for this instruction, or they can use it as an operand. 2 of the methods that are used to fetch code are found in branch instructions, one of them, and in jump instructions, the other one. What's the name of the addressing mode that we use in branch instructions? Relative to what? Relative to PC. That's right. Whatever the program counter value is now, plus or minus some amount, tells me where to branch to. So that's called the PC relative mode. Now in jumps, we jump much further away. In theory, branches will be close by, but jumps can be much further away. So this sets a limit of 16 bits of FARC, in the relative part, because it's only a 16-bit field. So if we're going to jump, the PC relative mode wouldn't allow us very much freedom to move far away from the current value that we're fetching and executing. So we use a different mode for jump instructions. What's the name of that addressing mode? If it was a 32-bit address and you said here, jump there, we would call it direct. But since it's not a 32-bit address, our field is only 26 bits, we call it pseudo-direct. Pseudo-direct, okay? That's the name of the... Okay? Well, those are the 2 ways to go to a different address when we're looking to fetch code. Now let's talk about for data, okay? Now this one is even easier because there's only 3 places that my data operands can be found. What are the 3 places that my data operands can be found? In registers, that's one good place. In memory, that's another good place. Cache is a form of memory, so that's 2. And the third one is? We can't fetch anything off a disk, no. In the instruction itself. So in the instruction is one place data can be put. When it's in the instruction, what kind of operand do we call that? An immediate operand, right? So therefore, for data, one of our addressing modes is known as immediate addressing mode. That means the thing you want is right in the instruction. Okay? Another of our addressing modes, when we get it from register, is called register mode. Yep, that's pretty easy too. Register mode. Okay, so add I T0, T0, 2. The 2 is right in the instruction. Add T0, T1, T2. The operands are in registers. And the third location, of course, in memory. Anybody know what we call that addressing mode when my operand is in memory? Yeah, because I use a register as the base address to go get it from memory. So it's called base, or sometimes base plus displacement mode. And that's when you address like this. Go to register T0 and get that value and use it as an address. Oh, and by the way, add 4 more to it, and that's the address in memory that I want to get the operand from, right? So you've seen that too. So we've seen all these modes. If you want to get data, it's either in the instruction, use immediate mode, or it's in register, use register mode, or it's in memory, use base plus displacement mode. If you want to get an instruction, it's in memory, it's nowhere else, so you either find its memory address using PC relative, or you find its memory address using pseudo-direct. Okay, now let's talk about the relation between these modes of addressing and our 3 instruction formats. If you remember, I have 3 instruction formats, R, I, and J. Remember that? They all have a 6-bit opcode in the beginning, and then what comes after that can be quite different. This one has a 16-bit field here. This one has a 26-bit field here. And this one has got a register, and another register, and another register here. Okay. If I want to use the PC relative mode, what kind of instruction would be wanting that mode? If I want to use the PC relative mode to address the next instruction, what kind of instruction would be doing that? A branch instruction. And what format do the branch instructions have? I format, that's right. So that means that this becomes the relative part, and I add that to the PC value that I have. If it's negative, I branch backward. If it's positive, I branch forward. Good. What kind of instruction would want to be doing a pseudo-direct address of the next instruction? A jump. So what format should I be using for jump instructions? J format. Okay, good. What kind of a instruction would we be wanting to do use immediate mode? Hello? What kind of instruction would be wanting to do an immediate operation with the immediate value found in the instruction? What kind of instruction? I didn't ask what format. What kind of instruction? Immediate instructions. Add immediate, or immediate, subtract immediate, those kind of instructions, right? So therefore, what format are those instructions? They're I format, aren't they? They're going to have one register. Oops, I didn't quite draw this right. There we go. They're going to have one register, which is my source, and they're going to have an immediate, which is my second source, and one register, which is my destination, just like you see here. One source, an immediate second source, and destination. So this has to be I format because this thing can take up 16 bits. So it only fits this format right here. So those are I format. Okay, what kind of instruction would be doing register mode addressing? Register mode addressing. Add, or, sub, shift, those kind of ones. And those all fit the R format. Okay? So the R format instructions use register mode, and register mode for the three references. Technically speaking, this instruction uses immediate mode to get that operand and register mode to get that operand. So technically, to go get the one that's referenced here, it's actually using register mode for that, but immediate for the immediate operand. And finally, the last one, base plus displacement. What kind of instructions need to go to memory to get a data value? Loads, exactly. And what kind of instructions need to go to memory to store a data value? Stores. And what format do loads and stores have? I format, yeah, okay. So I think we could say that the most general purpose and heavily used format is actually the I format because it helps us with our branches, it helps us with our memory loads and stores, and it helps us with our arithmetic and logical immediates. Works with all kind of different instructions, okay? Change of control, go get data out of or put data in memory, and go get data immediately out of the instruction, okay? The R types are more specific, where I know my two source and destination operands. The jumps are more specific, okay? The I types are more versatile. That format is used for a variety of different instructions. Yes?
Can you give me about the pseudo-direct an example?
Sure. Sure. J integrate. What does that mean? What does that mean? Jump to?
Integrate.
What is integrate? Yeah, there's a label somewhere in the code named integrate, and if I jump to that label, what am I probably going to find? What am I probably going to find? Yeah, code which performs numeric integration, I guess. It seems to, it's claiming that it can integrate some things, okay? All right, so here's the code for J. That goes there. Now you tell me, what do you think I should put here in the 26-bit field? Address of integrate. Yeah, exactly. The address of integrate. Notice I put integrate colon, indicating that it's an address in the program. It's a label telling me at this address you start the code which integrates. Now the only problem is what? That's a 26-bit field, and integrate, like all addresses in MIPS, is a 32-bit address. So we have a little bit of problem of 6 bits, don't we? That's why I don't call it direct addressing. If this was a direct 32-bit address for integrate, I put it in, go there, it's finished. It's not pseudo. The reason it's called pseudo is because of those 6 bits. Okay? We've got to play some kind of an Udurma game to get it where it's close enough. Okay? So You can read about that in the text if you'd like. Basically what it does, it adds 2 zeros at the end. So now I've got 28 bits. Why did I add 2 zeros? Because all addresses of code to be fetched begins on an even word boundary. We never begin on cipher beer, beer cipher, or beer beer. We always begin on shift cipher. So 0, 4, 8, C, 10, etc. Okay? Yeah. That gets us to 28. What about 32? I still need 4 more bits. Okay, what I'm going to do here, on the upper end, I'm going to paste in PC 31 to 28. Those bits are going to be pasted right here. So the upper bits of my current program counter are going to be taken as is and yapishtered with the 28 bits that I got from the instruction, giving me 32. Is it a direct jump? No. Is it a pseudo direct jump? Yes. Okay. All right. Any other questions? Let's move on to new material then. All right. Let's pick up where Özcan Hoca left off in the last lecture. Oops, a little too far. Yeah. Okay. This was the last slide that you looked at. Am I right? The one in yellow? Yeah. Okay. All right. So what are we doing here? We're working on the swap procedure. In C, it's a non-leaf because sort calls swap, as you can see here. So sort itself calls a procedure called swap, which was written on the earlier. And so here's the procedure body for sorting. All right, and let's see if we can make some sense out of this. Okay, it's got 2 loops, an inner loop and an outer loop, and most of the code is just getting ready to do the loops correctly, as you can see. If you do the inner loop, you jump to 4, 2 test and go back to here. So the inner loop runs here. We branch out here to exit to if we go out. The outer loop, exit to says come in here if we branch to there, and then jump to 4, 1 test, which takes us back to the top. And the only way out of that is here. Okay, so both loops end with a bottom jump back to the top of the loop. The inner loop exits only to the outer loop, which makes sense. When the inner loop finishes, we say, great, now go back and pick up the outer loop at the place that you were calling the inner loop. So if you, see the 2 for loops. For I equals 0 up to n incrementing I, for j equals I minus 1, do these things. And the, the inner loop begins here and ends there. So the outer loop actually contains do the inner loop and then do a swap. Do the inner loop and then do a swap. That's the definition of the outer loop, is do the inner loop and then swap and go back and do the outer loop again, do the inner loop and swap. Okay? So that means that we need to have a code architecture that looks like this. Obviously there's parameter passing. You can see that we jump to swap right here before we finish up our inner loop. So the swap is inside the inner loop. And then we do an incrementation of S1, which is our J value, decrement our J value, and jump back to the test of inner loop, where we actually test and see, as is shown here, the inner loop's test needs to be, the inner loops test, hold on. Yeah, here it is. This is the initial condition. This is the test condition. This is the increment condition. So we have to run this test every time we run the inner loop. Is this side greater than this side? If not, then we leave the inner loop. All right, I'm going to challenge you to look at this and study it in your book. There isn't any substitute. I can sit here and talk for a half an hour, but unless you've actually put in intellectual mental time wrestling with the code and thinking through the logic and comparing high level to low level, you'll not understand this. So I'm not going to say anything more than just to say that you need to study this. Okay? And we're going to go on and do another example, but I want to say this is a reasonably complicated case of compiling nested loops with Reasonably clear code, lots of nice explanation. I think the main things I would point out to you here are every line has got an explanation. The lines are grouped and the groups have an explanation. So this is about as clear of assembly language code as you'll see. Obviously you don't start here. You first start by understanding very well what this does. Okay? If you have trouble with that, there's no hope of understanding how it's implemented in assembly. So first you have to understand what this is doing. How does this do the sorting program? Okay? Then after that, then work your way. Notice move parameters, outer loop, inner loop, pass parameters and call, end of inner loop, end of outer loop. Okay, so we can see that the inner loop is actually from here to here. The outer loop surrounds that and is from here to here. This is the initialization of the whole thing as it's begun. Obviously our initial parameters in A1 and A2 are pushed into S so that we can use them safely. All right. So the full thing, when you package that inside this, looks like this. Make room on the stack, because sort has been called, for how many places? 5, right? Push, 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 push. The current values of RA, S3, S2, S1, and S0. Can anybody answer the question, why am I pushing this? Why am I pushing that, pushing that, pushing that? Let's answer the question. In your mind, are you clear on why do I need to preserve this on the stack and then pop it back off later? Why do I need to preserve this on the stack and then pop it back off later? The yellow code here that you see goes right here. It's the actual activity. But before you get into the activity, there's this setup and takedown. Why are we doing that? Why are we doing that? Why bother to save anything on the stack and then pop it back off? It looks like a lot of time spent and extra instructions. Is it valuable? Is it necessary? Do you have a good answer for that inside you? Some of you do. You're answering out loud even. But I'm wondering, does everybody have an understanding of why you would preserve something on the stack? What's your name, sir? Salatin. Today's your lucky day. Salatin. Why do I want to preserve these 4 S registers on the stack, push them on before I do any work, and then pop them back after I've done the work? Why would I do that?
I have no idea.
No idea. Okay, that's what I thought. Raise your hand if Salatin is actually a representative of you. If he's honest, because I asked him, but I didn't ask you, but I'm wondering how many people here are like Salatin, really don't know why we're bothering to push things and pop them back off. Don't really know. Okay. Let's look at the code in yellow, just briefly once again. And let's say, Salatin, since it's your lucky day, I'm going to continue to let you be the big Piongo winner today. Salatin, do you see any places where the value of S0, S1, S2, or S3 gets changed by an assembly language instruction? Yeah, and that's pretty easy to do, isn't it? Because we just scan down here. Everybody pretty much knows that except for store words, things start on the right side and they change the value on the left side, don't they? So here's where S2 gets changed. Here's where S3 gets changed. Here's where S0 gets changed. Here's where S1 gets changed. So in the first 5 lines of code, 4 of them got changed. So what would happen if I didn't push them on the stack first? If I don't push the value in S2 on the stack first and I do this, what happens to the old value? It's overwritten, isn't it? It's gone now. Okay, if I push the value of S2 on the stack first and then do this, now what situation do I have? Old value of S2 is in the stack, but S2 itself now contains a new value, which I then am going to use. If you look around S0, S1, S1, S2, they're used on the right-hand side, and so that allows me to use S2, but also save the old value and then bring it back at the end. Why would I do that? Why not just destroy it and say, Boschwer Gitzen? Okay, he's not sure about that. Do you have any idea about that question? Why is it worth it to save the value?
Maybe we can need that values for another functions.
Such as? Who?
The other loops.
Other, meaning ones we see here or ones we don't see here?
Yeah, an agreement with computer that nobody touches.
Yeah, okay, now Ur is saying, well, wait, there's this Uluslar Arsa Anlaşma, and it says you don't change the values in S0, but I'm going to ask you a question. Kim o anlaşmayı imza etti? Attı bizim ülkemizin adında. He? Dış işlerimiz, dış politikamız, yani ne haline geldi böyle bir imza atacağız ki? Yani, yani, değil mi? Okay, why does that anlaşma, that agreement make any sense? To preserve the values of the S registers. He's right. There's a promise. You signed up. Yeah, we will not destroy the values of the S registers when we use them. We will save them first and then restore them later. But why? Countries ask, why are we in this treaty? Well, 100 years ago, our king signed up and we're still in it. Is it a good treaty still today? Should we renegotiate? Well, that's what I'm going to ask you. Do you have any idea about that? Why preserve the values of the S registers? Okay. Do you have any idea about that? Why preserve the values of the S registers? You? No, you. No, her. Yeah.
Maybe we need to use this S0 or S1.
Or S2 or S3. For another?
Function.
Yeah, and another function. What other function? Functions I see here or functions I don't see here? Don't see here. Such as, can you give me an excellent example? Such as the caller. Let's don't forget, my friends, that this whole thing is a callee. Somebody called sort. And so when somebody called sort, that means go here and start doing this. When it's all done, what are we going to do? Go back to the callee, and what are we going to say? Oh, excuse us, you had valuable things in the S registers, but we really stomped all over them, spit on them, and wrecked them, and too bad for you, they're all changed. Is that what we're going to say? Of course not. Of course not. It's our responsibility to preserve the value of the S registers. What's the name for the group of 8 S registers? They have a special name. Saved registers. Yeah, what is that? Muhafaza edilmiş, saklanmış, yani korunmuş olan, right? Yeah, the saved registers. So everybody can now see that I'm saving the saved registers. Great. What about this and this? These are different, though. Right here, that and that. Those are different. The RA and the RA. That's not a saved register. That's a return address register. Why am I bothering to push that on the stack and then take it back off later?
Because we need to return.
Because we need to have the right value here so that we can use it here. Well, let me ask you, do you see anything here which changes the value of the RA register? Do you see anything here which changes the value of the RA register? Do you see anything here which changes the value of the RA register? Look down here. Yes, JAL. When you jump and link, you destroy the value in the RA register. What do you put into the value of the RA register? When you do this jump and link swap, what do you put into the value of the RA register? This address right here of the next instruction. What did you destroy? Whatever was in there. Too bad, Zavala. We wrote over the top of it. How are you going to prevent destroying it if you write this address into it as part of this instruction? The only answer is because you were clever and you said, before I get into this, I'm going to push it on the stack, and after I get out of this, I'm going to pop it back off the stack. So now this is a true return. Let me ask you a question. If I didn't push it here and didn't pop it here, where would I go when I do JRRA? You know where I'd go? I'd go to right here. Is that where I want to go? Is this who called swap in the first place? No, I mean called sort? No, of course not. This is not who called anything. But that's where I'll go, because that's the return address value that's going to be in here from here, and still be in here when I return here, and still be in here when I leave that last line and go to here, 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 and still be in here. And if I don't do that, it'll still be in here, here, and I'll go back to right there. And that's not what I want to do, is it? No, it's not what I want to do. Okay, so we've seen the purpose of saving the S registers and the RA. And obviously, if I change the stack pointer by subtracting 20, I better change it back by adding 20 so that it's also left the same as it is. So that when I return here, I've done such a nice job house cleaning that everything is back the way it should be. The S registers are just as they were when sort was called. The the RA register is just what it was, etc., etc., etc. Okay? The stack pointer, they all have to be, so this is called housekeeping. You must do this when you call a procedure, especially if it's a non-leaf procedure. Okay. Any questions about this? Again, about procedure calls. So important to get this right. All right, let's look on. You all know about different sorts. I'm sure you've seen in your algorithms class, probably CS-101, 102, certainly CS-201, 202. You've seen that there are good sorting algorithms and better sorting algorithms and great sorting algorithms, right? Yes, you know that there's performance differences. In fact, the performance differences can be easily summarized by something called big O notation, right? And you know that this involves the number of steps that have to be executed in order to do the sort, okay? Number of steps at a high level. Well, it turns out number of steps at high level is directly proportional to number of steps at a low level. So if you have a bad algorithm, no amount of clever assembly language writing or optimizing compilers is going to save you from a bad algorithm. You're just going to have a slow algorithm. So let's look at bubble sort, which is also known as an exchange sort, and compare it to quick sort. Raise your hand if you've heard of bubble or exchange sort. Raise your hand if you've heard of quick sort. Okay, good. Most people have heard of both of those sorts. And I think you have an idea that quick sort is an improvement on exchange sorting. I hope that's something that you've come out of your algorithm classes with. Bubble sorting is slow. Quick sort is an improvement on that. There's even faster radix sorts and other sorts. Raise your hand if you feel that you have some modest amount of knowledge about sorting. Yeah, when people talk about sorting and big O notation, you're not ignorant. You can listen to the conversation, maybe even contribute something. Raise your hand if you're at that level. Okay, that means if you didn't raise your hand, you still feel yourself fairly ignorant of sorting. You really don't have confidence to understand, to talk about sorting. All right, my friends, sorting is a really key operation in computing. Maintaining sorted lists and sorted databases and sorted everything is really important, so therefore sorting is done all the time. And if you feel yourself after 4 courses still to not understand sorting very well, all I can do is say, go back and study, go back and study, go back and study that, and get it so that you don't stay zaif. So sorting is so fundamental that it's important that you understand it well to be a computer engineer, okay? So some of you did not raise your hand now. You don't feel conversant about sorting. I'm going to have to go ahead, but I'm going to refer you back to your material in 101, 102, 201, and 202 about sorting until you find that those algorithms become something you understand. All right, let's look at an example of comparing bubble sort with quick sort, right? And to sort 100,000 words in an array that's initialized to random variables on a Pentium 4 with a 3 gigahertz clock rate, 533 megahertz system bus, and 2 gigabytes of DDR-S DRAM using Linux version 2.4.20. Do you notice that everything's specified? Operating system, how much RAM, what the system bus rate is, the execution rate of the processor, which processor, you know, and even the random initialization. Now, when you take the code to do exchange sort and run it through a compiler, it's written in C, and you run it through a compiler, you can set optimization levels. You can ask that compiler to improve the quality of the outputted low-level code, okay? Improve the quality of the low-level code for this Pentium 4. So you can have no improvements, or you can ask it to do optimization level 1, or optimization level 2, or even optimization level 3. So we should expect that as we go this way, we're going to get better code that's going to run faster. And so the relative performance, as you can see, yep, does go that way. This gives 1.0. This is 2 times faster. This one's getting closer to 2.5 times faster. Notice that the optimization levels themselves have small differences, but no optimization is clearly way worse than turning on the optimization switches. Okay, so compilers have the ability to gain you some speed by better code that they output. You wrote the same code as input. It gave you slower or faster code as output. That's the first column. How many cycles it took to execute this sort is measured, right? And you can see that it gets to be less and less. That's where these numbers came from. Number of cycles at a given clock rate, that's going to tell us how much time. Number of instructions that were actually executed, and cycles per instruction. Do you notice that number of cycles per instruction actually rises here and then starts to shrink back with these optimizations? The unoptimized code has the best cycles per instruction. The 01 version has the lowest instruction count, but the 03 version is ultimately the fastest, because clock cycles multiplied by the clock rate tells you how much time. So this is the fastest, and that clearly shows that it was. Okay, now that's just bubble sort. Now, if you take that information and put it on these graphs, you see this kind of thing here. And relative performance gets slightly better to 03, but you notice the slight is so slight you can hardly tell it. The big change is to optimization. The ramping here that you can see is too small to even notice there. And the others are plotted here as well. The big change is from no optimization to optimization. Look what it did to the instruction count. When you optimize, you get so much less assembly language instructions from the same amount of high-level instructions. That's something very important to know. Okay? All right. Now, let's compare performance for two different sorting algorithms in C using Java. C and Java. Bubble sort versus quick sort. Okay, so you can see that for C versions, namely no optimization, optimization level 1, 2, and 3 are shown. For bubble sort in this column and quick sort in this column, and you're looking at relative performance. And then 2 for Java, interpreted Java and compiled Java with just-in-time compilation of the hot or frequently used Java modules. So what you can see is that the value of bubble sort, if this is the standard, the same numbers that we saw last time, and then compared to that, interpreted Java is way slower than compiled C, 8 times slower than compiled C. Is there anything we can do to speed up Java a little bit? Yeah, we can pre-compile the crucial aspects of the code, and notice it gets in the game. So for bubble sort, Java can be in the game, but only if you're using the JIT compiler. If you're interpreting Java, you have the classic compiled is fast, interpreted is slow. All right? That's the first thing to notice. That's just for bubble sort. Now, if we look over to quick sort, again, the performance with no optimizations on the of C of the quick sort algorithm, let's call it 1.0. Okay? And then from there, if we turn on the optimizations, we can almost double that with 03 level. Java looks really bad, 20 times slower if we just interpret it. If we turn on the Java compiling, we speed up by a factor of about 6, but we don't really get in the game. So for some reason, compiled Java runs pretty good in bubble sort against the alternatives in C. It doesn't run very good in quick sort. Something about quick sort and the way that algorithm runs doesn't really help. Compiling Java doesn't really help us very much here. So you can see that the winner again is optimization level 3 C compiled code for quick sort. Then the next question is, how about bubble versus quick sort? So now, since these are just normalized, they don't really show which is faster. But if you take actual time or cycles and compare them to each other, we find that the speed up of using quick sort is 2,400, almost 2,500 times faster. You can sort in quick sort, these 100,000 words, 2,500 times faster than you can do them in bubble sort. How about if we go to optimization? Well, after we optimize this and optimize that, 1,500, almost 2,000. How about if we simply look at slow Java bubble sort versus slow Java quick sort? Java still says it's 1,000 times faster in quick sort. And then we go to compiled Java. It's still 338 times faster. Notice we didn't get a big speed up here, so we lost some of our performance here. All right, so what does this chart say? It says quite a few different things. We're calling this the effect of language and algorithm. Okay, bubble sorts, relative performance in the 6 language and compiled options are shown on the top there. The quick sort relative performance are shown there. Those are these 2 columns here, that and that, are shown there. The third one is the bubble sort versus quick sort speed up. And you can see, that's the final column that we showed here. Just in graphical form, the same thing in case you are more of a visual learner. Now let's ask. The first thing that we notice from this, from the first slide and the others as well, is that instruction count, how many assembly language instructions it turns into, and cycles per instruction, CPI, are really not the good performance indicators in isolation by themselves. Time is. And in this case, cycles, because the clock was a fixed rate. So if you know cycles, then you know what the cycle time is for one cycle. If you have a gigahertz clock, it's 1 nanosecond, whatever. You figure, so cycles tells you time. And so time is the actual, faster means less time, slower means more time. The second thing is we see that compiler optimizations help, but they're sensitive to the algorithm. You go here, you can see that we didn't get the same gain when we optimized quicksort as we did when we optimized bubble sort. Look, optimizing says, oh, it's 1.5 times faster. Here it says it's nearly 2.5 times faster. So optimizations are sensitive to the algorithm itself. Some optimize better at low-level code than others do. So you don't expect the same gain every time you optimize. Third thing is Java with JIT, just-in-time compiling, is way faster than just interpreted Java using the Java machine. We saw that in both of these cases. When we compile, we had this huge gain. When we compile, we had this huge gain. Not so huge, but we had gains. So compiling Java is the only way to save it from, pitiful slowness. Okay. Then the next thing to notice is that sometimes, not in both algorithms, just in bubble sort, compiled Java got close to compiled C. Okay? In some cases, compiling Java gets it near the game with compiled C, but not all. Not all. And the last thing is, I think that's the crucial point here, nothing can fix a dumb algorithm. If you're using bubble sort, you just can't win, because people that use quicksort are going to be anywhere from 300 to 2,500 times faster than you, because you have a bad big O in the first place. So what are we doing here with languages and with compiler optimizations? We're tinkering with the Katsaya factor, but we're not playing with the big O. The big O comes from the algorithm itself. Right? So the speedups that you saw, even as high as 2,500 and 2.5 and things like that, not 2,500, that was the big O issue. But the Katsayas that you saw there, those were optimizations that can be obtained at the language level and the compiler level. And if I were writing a code, I would say, well, it looks to me I ought to choose C over Java, and I ought to turn on my optimizer to the max and squeeze out the very fastest code that my compiler can give me. And if somebody comes along and says, well, we're selling a compiler that has 04 and we can do better than the one you're using, I'd say, I'm all ears, I'm interested. What can you do for me? What's the performance improvement going to be? And they say, well, we can get you to 2.42. Well, how many thousands of dollars is it going to cost for your WYSI compiler? We can get you to 3.42. I'm all ears. I'm all ears. What's the performance gain for the cost I'm going to be spending? But I think everybody sees that non-optimization leaves you with a missing performance you could have had. And non-compiling Java is just foolishness. Just foolishness. To run Java interpreted on the Java virtual machine is foolishness. But above all foolishness is using a dumb algorithm when there's a better one available. That's the greatest foolishness of all. Okay, let's take a break. Thank you for your good attention. We'll come back and continue after the break.